Electrolysis and other processes. We have been studying voltaic cells which work as a result of a spontaneous reaction. However, we can also use energy from an outside source to make a non-spontaneous reaction take place. Driving a chemical reaction by using outside electric energy is called electrolysis. A cell in which this occurs is an electrolytic cell. Also, applying a reverse voltage to a voltaic cell can recharge it by running the spontaneous reaction backwards, replenishing the electrodes and ions. This is the basis for rechargeable batteries. In electrolysis, or when recharging a battery, an external voltage, larger than the cell potential, is applied in the opposite direction from that of the voltaic cell. That drives the reaction in the non-spontaneous direction. By definition, the electrode at which oxidation occurs is always called the anode, and the electrode at which reduction takes place is always called the cathode. The external voltage, therefore, will reverse which electrode is which, since the reaction goes in the opposite direction. And the sign of the voltage will be reversed, since the external voltage supply determines that. So, in electrolysis, the anode is positive and the cathode is negative, the reverse of in a voltaic cell. Here's a side-by-side comparison of voltaic and electrolytic cells. And galvanic can also be used instead of voltaic. So, for our voltaic cell over here, we have electrons going this way, generating a voltage of 1.10 volts. Zinc is the anode because it's being oxidized. Cathode is the copper because it is being reduced. Now, when we look at the other one, electrolytic, what's the difference here? We have a power source greater than 1.10 volts. That will drive the electrons this way, which will also switch which is the cathode and which is the anode. Now, the copper is the anode and the zinc is the cathode. Another side-by-side comparison. We have the electrolytic cell over here, voltaic here. For the electrolytic, external energy drives a non-spontaneous reaction. Voltaic, energy is released from a spontaneous redox reaction. Surroundings, the battery or power supply does work on the system, which is our cell. Voltaic, the system does work on the surroundings, i.e. it can light up a light bulb. Anode at positive voltage, cathode at negative, and they're reversed here for the voltaic cell. What's the same for both of them, and this might get a little tricky. Anode is always where the oxidation occurs. Cathode is always where reduction occurs. In other words, the anode for a voltaic cell becomes the cathode for the electrolytic cell, and vice versa. Electroplating uses an active electrode to deposit a thin layer of one metal onto another metal object. In this example, silver will be plated onto the spoon. The spoon is the cathode. Silver is the anode. The solution contains silver ions that will be reduced at the cathode to metallic silver coating the spoon. So here's the ions being reduced at the cathode, and then you have the coating of silver on it. The anode is oxidized to replenish the supply of silver ions. To determine how much the mass of an electrode changes in a voltaic cell or electrolytic cell, 1. Measure the electric current and the time it has been running. 2. Determine the charge transferred with the relationship that 1 ampere of electric current represents 1 coulomb of charge per second. So Q is equal to I times delta T. Convert from charge to the number of moles of electrons by dividing by the Faraday. 96,485 coulombs per mole of electrons. Use the formula for the reaction to determine the ratio of the moles of electrons to the moles of the species of interest. And finally, use the periodic table to determine the mass of that many moles of those atoms or molecules. Let's work a problem. A 7 amp current passes through molten aluminum chloride in an electrolytic cell for 60 minutes. What mass of aluminum will be deposited? And here's our equation here. We're going to follow the step-by-step procedure from 2 slides ago. We start with the current. And we have delta T, which is 60 minutes. We need to convert that to seconds. So there's 60 seconds in a minute, so we have 3,600 seconds. We use our charge formula, and that's 7 amps times the time, and 25,200 coulombs have passed. Now we go to the next step to find how many moles of electrons. We have our coulombs here, we have our Faraday constant, and we get 0.261 moles of electrons. Now we need to know how many moles of aluminum. Well, we have the number of electrons already found, and what do we notice here? We have 3 moles of electrons for every 1 mole of aluminum. So that's this conversion factor here, and we get 0.087 moles of aluminum. Finally, we go to the periodic table, and we have 0.087 moles, and we have 27 grams per mole of aluminum. We get that off the periodic table. So we have 2.35 grams of aluminum deposited. A 2.0 amp current is generated by a copper-zinc voltaic cell. How much will the mass of the zinc electrode be reduced in 15 minutes? And here's our half reaction. We'll use the same procedure we just did for example 1. We have our current, we have our time in minutes, which we will convert to seconds, so we have 900 seconds. The amount of charge that's moved is I delta T, 1800 coulombs. Now we need to find out how many moles of electrons. Well, we have the 1800 coulombs, and then we use Faraday's constant to convert this to moles, and we get 0.0187 moles. Now we need the number of moles of zinc. Well, we go to our half reaction. For every 1 mole of zinc, we need 2 electrons. So that's what we have here, 2 moles of electrons. 0.00933 moles of zinc. And then we wrap it up by looking at the periodic table, where zinc is 65.4 grams per mole, and that works out to be 0.610 grams of zinc. We can also determine the time from the change in mass. And we use this procedure. Start with the periodic table to determine the number of moles of the mass of atoms or molecules. Step 2, use the formula for the reaction to determine the ratio of the moles of electrons to the moles of the species of interest. Convert from the number of moles of electrons to charge by multiplying by the Faraday. And finally, determine the time by dividing the total charge by the current. How many minutes will it take to plate out 6.36 grams of copper metal from a solution of copper 2+ using a current of 12 amps in an electrolytic cell? And we're given the half reaction formula right here. We start by determining the amount of moles of copper we have. So the number of moles is the mass of the copper divided by the molar mass, which we get off the periodic table. So 6.36 grams divided by 63.5 grams per mole is 0.100 mole. Now we have to figure out how many moles of electrons do we have. Well, there's 2 moles of electrons per mole of copper. So that's this 2. We multiply that by 0.100 moles of copper, and this is how many moles of electrons we have. Then we find the charge, which is the Faraday constant, times the number of moles of electrons. Here's Faraday, here's 0.200, and we have 19,300 coulombs. Finally, to find the time, that's the charge divided by the current. 19,300 coulombs by 12 amps is 1608 seconds. When you're using Faraday's, your answer is going to come out in seconds. And then we go ahead and divide that by 60 to find out how many minutes.